In this video, we'll continue our discussion of Green's theorem by working another example. So again, they gave me the circle here, so hopefully it is closed. It says the boundary of the triangle, and I went ahead and drew it because I get obsessive, so I'm going to leave it there. You can copy it. We're going to say that we go counterclockwise. So we have to, is it simple? The pink path, yes. Is it closed? Yes. Okay, and then that's C. And then my region R that it encloses, is it connected? Yes. All right, it is connected. Is it simply connected? Yes. Okay, connected, remember I can put 2 points in the region, connect them and stay in the region. Simply connected means I can put a path or some open space in here and contract it and stay in R. And that's for any open space I can put in R. So that file, this tells me I can use Green's theorem since I checked off all of those. So let's go ahead and start Green's theorem. This requires us to get the partial of n with respect to x. So n, remember this is m, this is n. Green's theorem required those two things. So derivative of n, partial derivative of n with respect to x is going to be 3x squared plus 3y squared. I'm going to scoot this over so I can put them both right here. Partial of m now with respect to y. All right, that gets me a 3y squared. And then the subtraction, so notice they're not conservative. We want to subtract these two things to put in my new integrand. And notice we just get 3x squared. All right, so since those, we have all these confirmed up here, we can use Green's theorem. So I'm going to rewrite my problem real quick. X is the teacher in me, I guess, probably rewriting my problems all the time. 3xy squared dy, and this is equal to the double integral over r, and then I put 3x squared in there because that's a subtraction, and that's dA. All right, we can see the bounds nice and easy. I'm just going to put them over here, okay, x and y. We can see y is going to be the easier one to make a fraction out of because this is just straight through the middle. That is y equals x. So it's going to go y equals x. I want to make sure that doesn't look like a negative. Y, that goes from here up, and that's y is x to 1, and then we can use x just 0 to 1. All right, so this thing is equal to, my x's go on the outside. Not much better there. Okay, 0 and 1. And then we go from y equals x to y equals 1. And then we put 3x squared in here. And we got to make sure our bounds are right, dy dx. And with some work, we'll find that the answer is a pretty 1/4. Again, Green's theorem really makes things easy. But you have to check off those things we did at the beginning. Simple, enclosed, connected, simply connected.